Okay, so let's continue with question 7. Right? So technetium-99m is a radioactive isotope of the element technetium. So M denotes a metastable isomer of technetium, meaning that it's an excited configuration. So the first thing we know is that you have your different, so you have technetium, right? Tc over here, and then it's metastable technetium with an M, and the metastable technetium is in an excited state. So yeah, so with this one, it decay to its ground state, right, and emit a gamma ray, right, and this decay has a half-life. And if you're not sure of the idea of half-life, briefly speaking, it is the idea that you have a pool of, if you have a pool of the things that's going to decay, so you have MC, let's say you have 100 of them, right? So the half-life is the time required, the time taken for this 100 to decay into 50. So when it becomes 50, then 6.01 hours will have passed, right? And after that, it will continue, right, to be 25, another 6.01 hours, and every basically half-life is this concept. In this time, right, the population like that would die down to this. Yeah, and so for the half-life, yeah, so that's that. Okay, then so we know that this MTC, metastable technetium, is used in medical diagnosis, and it will basically yeah, so how do you make this MTC is first made by creating an isotope of molybdenum, right, 99MO, and then this molybdenum will decay into MTC with a half-life of this. So what that means is that you have your molybdenum over here and decays into MTC that you want. And it'll emit some stuff also. Yeah, so that's why MO will eventually make MTC, and eventually MTC will decay into TC, which is why MO will eventually become TC. So this is the law for radioactive decay. So yeah, so this law over here is a differential equation, as you may know, and N represents the number of nuclei, the number of nuclei, like in this case 100, N represents the number of that substance that you have. So the N dt, right, is how this substance changes with respect to time, right? N is a function of time. So this tells you that how N changes with respect to time is equals to negative lambda of N. And what this means is that the more you have, right, if you have let's say at N at time 100, right, you have at time sometime you have 100, right, then it'll be decreasing by minus lambda 100, right, and then hence N will decrease, right, and that will cause the 100 to become smaller, right, becomes even smaller, and eventually you'll asymptote towards. So at first, right, when you start with a high population, high number, N, it decreases very fast, right? But as soon as you get to lower values, as soon as you get to lower values, the decay rate is going to decrease as well, right? Because your N is small, so your DNODT is small as well. It's going to asymptote towards zero. It's never actually going to ever reach zero, right? As mathematically, it's never going to reach zero, but it's going to asymptote towards it. So yeah, so the first step is that from this differential equation, we are asked to show that it's a solution to this is a solution to this differential equation. So how do you do that? So we can use the separation of variables. So we know that this is the differential equation we want to solve. So we bring n over. So like this equals to minus lambda dt. And if you integrate both sides, yeah, if you integrate both sides, then you get ln of n, right? Ln of n equals to minus lambda t. Okay, and that will give you n equals to e to the power minus lambda t. And of course, there's a constant here I forgot, right? Never forget your integrating constant. And this integrating constant would be e to the power of c over here. And what is this e to the power of c? What's the constant? The constant, if you substitute time t equals to 0, right, you realize that n at t equals to 0 equals to e to the power of c. So this is effectively saying that, and let's denote this n at t equals to 0 to be n naught, the initial number of nuclei at time t equals to 0, right, which is stated here. So this is n naught e to the power minus lambda t, and hence we have obtained the solution. And if you go ahead and substitute this solution, this function, right, n of t back into the differential equation, you realize that it is in fact satisfied. Okay, so that's how we do the first question. That's a normal separable differential equation. Okay, so then in the case of this complicated process over here, they tell us that they're telling us that the number of nuclei as a function of time is given by these three equations, right? Okay, so yeah, then we're asked to complete the missing table values over here. So we need to understand, we need to take a look at this function, right? We see that there's a lambda 1 over here, right? So there's a lambda 1, right? And this is lambda 1 over here, and this is lambda 2. So what do we need to do over here? We need to find lambda 1 and lambda in terms of the half-life. So we're given this information, we're given the half-life, we're given the half-life of the of um of the decay process, right? But we're not given the value of lambda. So we need to calculate the value of lambda from the half-lives that are given. So how do you do that, right? Well, the formula is actually just lambda equals to ln 2 over the half-life, right? But it helps to understand why that is so. So, oh, that's a bit weird. Yeah, it helps to understand why that is so. Okay, so to understand why, so you have e to the power minus lambda t, right? The question is, when you, when is this equals to half, right? This is equals to half. So when is this equals to half? It's equals to half when your t is equals to, so you to do it, you ln both sides. So this is the factor that reduces the initial population when you have n of t equals to n naught e to the power minus lambda t, right? So this is the factor that reduces the initial population, right? So when reduces it by half, how much time has happened? So to do that, to calculate that, you can, so this will be minus ln 2, and hence you have t equals to ln 2 over lambda. Okay, and at the same time, right, so this, looking from this equation, we know that the time that n naught, your initial population, has become n naught over 2, right? The time that has, at the time that has passed, right, this time that's elapsed, right, from the initial population to fall to half as original, is equals to ln 2 over lambda. But this time is is precisely the definition of half-life, right? This time is the definition of half-life, as I mentioned previously. So hence, this is just a t half-life. And hence, rearranging this, you get lambda equals to ln 2 over the half-life. So that's how you obtain, that's how you reason out from this equation. So over here, we're given two definitions, right? Or in a sense, two descriptions, right? One is the half-life and one is the equation. And we need to relate the two. And to relate two, we go through this process. Okay, so yeah. So with that, we can calculate our lambda 1 and lambda 2, right? So lambda 1 is referring to, okay, so somewhere in the question, they say that lambda 1, okay, so they do mention it somewhere. Let me just find it. Okay. Lambda 1, Okay, actually they didn't. I can't find the definition of lambda 1 actually. But lambda 1 is the decay from the molybdenum to the technetium. So yeah, so we know that that happens with a half-life of 65.9 hours. So this is your lambda 1 with your 65.9 hours, right? And this is your lambda 2 with 60.66.01 hours. Right. So so to calculate lambda 1, we just take ln 2 over 65.9 in the unit of hours, and we get 0.010516 hours per hours, right? So the units in the denominator is hours, so we get these units. So lambda 2, if you calculate it, will give you 6.01 hours, and that will give you around this quantity over here. Yeah, so so in order to calculate, so over here we have the constants, we have figured out the constants, right? And all that remains is, so we know lambda 1, lambda 2, our n naught, our n naught is simply 1000, right? Our n naught over here comes from 1000 because we know that that's when n1 at time t goes to 0. So yeah, so with that we can plug it all in, right? And we will get around 59, right, for n2. And for n3, right, we know that n3 is equals to 1000 minus n1 minus n2. So yeah, so that will be that'll be 41. Okay, so yep, yeah, that's right. Okay, so that's, we have done the first part. We've completed 2 missing entries in the table, and now we want to calculate the maximum time when maximum value of n2 occurs. So you see that n2 increases, and then after a while it starts decreasing again. So the plot of n2, right, looks something like that. Right? So when I calculate the maximum, and what do you do when you calculate the maximum? You differentiate the function. So you differentiate this n2 over here, you differentiate it. So you differentiate, and what do you obtain? Right, so the n2 over dt gives you yeah, so it gives you lambda 1. So the constant is just the constant, and n naught is just a constant. Then inside here you have 2 terms, right? You have minus lambda 1 e to the power minus lambda 1 t. Then you have plus lambda 2 e to the power minus lambda 2 t. Okay, so yeah. So now we need to equate this equals to 0, right? Because we want to find the maximum, right? And in physics, we don't need to do the second derivative test because, yeah, in math you need to, but in physics you don't. So getting rid of the constants, we note that lambda 2 e to the power minus 2 lambda 2t equals to lambda 1 e to the power minus lambda 1t, right? So taking the ratio, we can obtain ln of lambda 2 over lambda 1 equals to lambda 2 minus lambda 1 t. And we have all the constants that we need. We can substitute our lambda 1 and lambda 2, which we have calculated here, right? We have calculated here into this equation, and we obtain t equals to 22.8 hours, right? And we see that it kind of lies around here, which kind of makes sense also because 20 was the maximum, then it probably goes up a bit, then it goes down. So yeah, so the answer is 22.8 hours. Okay, so then the third part, we're asked to draw and label the best fit curves for each function. So I'm not going to plot all the single points, but the answer key looks something like that. Right, it looks something like that. And then this one will go up, and it maximizes at around, right? So it looks something like that lah. It maximizes around 28, right, and it goes down. So this is just a very rough sketch, right? Yeah, I'll leave it to you to plot it yourself. Okay, so after Now we have a qualitative question. Right? So after so just to mention, you're given 2 marks for the plotting of the points and 2 marks for the curves. One, I suppose, one for each. So now we are given that this question, right? Why is it not a good idea to have a radioactive isotope decay by beta decay inside the body? And this is the answer. You can go ahead and read it yourself. Yeah. Okay, so calculate the activity of using the data, calculate the activity of 99 TC at 150 hours. So okay, so 150 hours. Okay, so at 150 hours, okay, so yeah, so I was trying to find the half-life and so we're given that the half-life of we're given that the half-life of the decay is this many years, right? So this is going from TC to ruthenium. That's right. So from TC to ruthenium, you have it takes it takes that it takes the half-life is 211,000 years, a very long time, right? And we need to calculate activity of this TC thing at 150 hours. So what is the first activity over here? What is activity is the number of decay, right, events happening per second. So what this means is that at this instance, right, I have some amount of TC, right? Let's say I have 200, right? Then after some time, right, after 1 second, right, in 1 second, let's say I have 199, then the activity is going to be 200 minus 199 divided by 1 second. So that is activity. So of course, if this was to if the activity was changing very fast, right, then measuring the time interval when it's at 1 second wouldn't be ideal because perhaps the activity at, let's say, 0.1 seconds was very fast, was very high, then at, let's say, 0.9 seconds is very low. So what they're actually asking for is we're actually supposed to take the derivative of n. So they're actually asking us to calculate the derivative of n dt, right? And this is going to be a negative number. So they want us to calculate the absolute value of it at time t equals to 150 hours, right? So so that's why it is mathematically. So how do you calculate it, right? This is just equals to, so given we know the function, we know that n of t, n of t is, it follows this pattern, right? So this, if you differentiate it, right, then you're gonna get e minus lambda n, right, at t equals to 150 hours. So yeah, so we need to calculate, so we need to know, so this is, the answer will be equals to minus lambda, right? And this is m naught e to the power of minus lambda 150 hours. Okay, so we need to know a few quantities over here. We need to know the lambda, and we need to know the n naught, right? So yeah, so how do you calculate how do you know what the n naught is? We can look at a table 7.1. At table 7.1, we know that at 150 hours, right, n is 773, sorry. So 773 is n3, which is the number of technetium nuclei, right? So that's what n naught is. Yeah, so that's what n naught is. So we know n naught already. And sorry. That's not what n naught is. That's what n naught times this entire thing is. Yeah, this entire thing is 773. Yeah, so that's what it is. Because n naught is the initial number, but at 150, right? At 150 hours, it is this amount left over. So then what is lambda, right? Lambda can be calculated by using the information of the half-life over here to calculate it. So lambda is equals to, lambda is equals to ln 2 over 21100 years times 365.25, right? Days per year times 24 hours per day times 3600 seconds per hour, right? And then so that's the lambda over here. What we written is just lambda, and now we multiply by 773, which is the number of technetium nuclei at 150 hours. Yeah, sorry, it's not n naught. Okay, so we don't need to calculate exactly n naught, but as long as we know n naught times this number over here, we can so if you calculate that, right, then that will give you 8.04 times 10 to the power minus 10 decays per second. But what's the unit for decays per second is BQ, becquerel. Yeah. So that's how you calculate the activity. So suggest why, now moving on to the next part, suggest why this radioactivity is not sufficiently harmful, right? It's because the background radiation itself, we are always constantly being showered by around 20 becquerel. So this such a small number is going to be insignificant if added to 20. Yeah, so with that, we're done with question 7, right? Yeah, and I'll see you at question 8.